All right, hi guys. So today what we're going to be doing is we're going to be doing lesson 413. So hopefully the sub has let you know that that we're not doing 423, but we're going to do 413. So it's going to be a little different on the calendar. We're just going to basically switch around. I think it's like Monday and Thursday or Monday and Wednesday. So we're just going to flip flop them. So the homework that you're going to have tonight, we're not doing tonight. You're going to do 413's homework, which is like problems 1 through 6 in this section. So. We're going to go through a warm-up. Remember, pause the video at the warm-up. I'll even say it. All right, make sure you have your calculator out. Make sure you're taking notes. And if you are really struggling with this, all right, make sure that you're going back through this lesson, kind of looking at what I do, what I say, because I too, need to make sure that I keep going through this to make sure that I have it mastered. One more thing from the homework from Friday, I put the answer key on Classroom. So you should see it up there. It's a 412 answer key. So take a look at that. It's identical to the back of the book, but I actually show work on there, so you can take a look at that, okay? So here we go. Let's get started. So, all right, in your book on, here we go. Let's just do whatever page is right before 413. I don't even have something on here, okay? Here's your warm-up. It says, some cars in a school parking lot have the following license plate identifications. Use this list and the information that follows to complete the problems 5 and 6. So I got those problems down here. It's really not 5 and 6. It really should be 1 and 2. All right, so there you go. Error number 1. So anyway, you're going to do these two things. So basically, you're going to draw a Venn diagram, and then from there, what you're going to do is you are going to describe those two events, not V or V naught, and then V intersecting S. All right, so I'm going to put this like this, and I'm going to want you to pause the video right now, and I want you to try to create that Venn diagram, and I want you to describe the events, basically tell me which license plates are in each of those events and list their outcome. Okay, so pause it. Try to do this and then start it back up, and then you'll see the answers. All right, pause. All right, so here we go. So here are the solutions to this. So you're going to see that I took each of these different events, choosing the license plate as at least one vowel, and the sum of the digits. I've circled those with different colors. So I got the purple, and then I got the orange. So you can see on here, I went through each one individually, and I said, all right, which one has at least one vowel? So I went through it. So that's the third one, this guy right here. I'm clicking on it, you can't even see it. So the third one, the fourth one, the sixth one, and the seventh one, and then the sum of the digits. So really, you're just taking the digits, and they got to be greater than 20. So that's the second, third, and the last one. All right, those are the ones with the orange on there. So identifying that first actually can help you out to make your Venn diagram, because now when I made my Venn diagram, all right, again, I make my big sample space. All right, so I make this nice and big square. All right, and then I put my two circles. Now my two circles are for my two, excuse me, for my two events. So I got vowels. All right, so my vowels in purple, and my sum is in orange. So I put those that fit just for the vowels in the vowel side, those for the sum and just the sum side, and those that shared both vowels and sum, I put those in the middle, and that's their intersection. Now, any license plate that didn't have anything, for instance, this guy and this guy, if you look back up on the original form, this thing had nothing on it, and this thing there was nothing about it. So because it didn't fit in one of the two events, we put that still in our sample space, but that's kind of on the outside, but still within the box, because you need to make sure you have that. So then the second one, it said describe the events V not. So not being in V means that you're anything but V. So whether you're in the intersection or you're in V, we're not including those things. So you're going to have three things. You'll have B, C, F, whatever those numbers are, KXL, whatever those numbers are, and MRB, whatever those numbers are. All right, so those are in V not. And then for the other one, for the other sample space or the other event that we're trying to talk about, that is V intersecting S. That's what they have in common. That's the middle part. So V intersecting S, this guy right here, that's this middle part. So we're the two things that they both share. So hopefully you're able to do that. Hopefully now you look at it, you're like, oh, okay, that totally makes sense. And then you're ready to go. All right, so homework questions, that's funny because I can't answer any of them. But this right here, you can see this. All these answers are on Google Classroom, so take a look at that. You can check them. Anything, especially if you had been going back and forth between the answer key and these problems, you can look at these and you can kind of see and work your way through it. Now, again, you know, even if you didn't do it, you can still go back through this and practice, because that's the big thing, is just practicing. Practice, all right? So these are all there, so I'm not going to go through that. You can check that on your own time. What I want to do, come on now, one more. All right, is I want to talk about what we're going to do today. So we're on lesson 4.1.3. So if you haven't figured that out yet, you got to find 4.1.3 in your book. I will have the page number up in a second. That's where we're on today. And we're going to talk about independent events, identifying whether or not events are independent, and then really then determining, all right, well, if they're not independent, they're dependent events. That's how you're going to really figure this out. And then we're going to use the independent event formula to determine if events are independent or not. So independent events, what does that mean? Well, here we go. So on page 36, you're going to take these notes here, okay? So if you need to pause the video, pause it to write it, and then you can listen to what I'm saying while I'm going through it. So independent events is one event does not affect the other probability, or the probability of another event. So one event does not affect the probability of another event, all right? So what that means is, for instance, me not coming to school, so that's one event. Me not being at school today, does that affect what's being served in the cafeteria? And odds are that doesn't. All right, the cafeteria people and I, we have nothing in common. I don't go down there, so there's no connection. There's no reason why me not being there will affect that. So those are independent. Whereas a dependent event would be like me not coming to school and you having to listen to me talk to you on Google Classroom. Those are dependent. I not being there requires you to have to listen to this on Google Classroom. So that's dependent. So independent means it does not affect the other one. Now, this formula right here, all right, this guy, this is another formula that's going to be very important here. This is the independent events formula. So what it is it's read like this. So the probability of A intersecting B, oh man, come on, dude. All right, so the probability of A intersecting B, so the probability of A and B occurring at the exact same time is equivalent to the probability of A times the probability of B. So you multiply those together. If that is true, that the probability of this guy and the probability of these two being multiplied together are equal, true, that tells me our two events, A and B, are independent. That doesn't even spell it, but whatever. All right, so if these two are equal to each other, when you multiply the probability of each one individually, and it equals the probability of both happening at the same time, then they are independent. Now, if you get a false statement, that means it's dependent. All right, so if you get the intersection of A and B not equaling the probability of each one independently, they're not relying on each other. They're not independent. They are dependent. They rely on the other one. So basically what you're going to do is you're going to get these three different probabilities, and you're going to identify whether or not you get a true or a false statement. That's what the independent events formula is. You're going to use that to see whether or not well, two events are independent or dependent. So here we go. Let's go to the first thing. So today we're going to start with the warm-up. All right. So now the warm-up isn't really talking about independent or dependent, but it kind of gets you started and thinking about certain things. So, all right. Oh, I should read this to you. All right, so it says Tanya's class is studying probability by playing games or conducting probability experiments. Tanya can choose one of the three experiments to do. So dice, flipping a coin 3 times, or spinners. If she gets an outcome with all matching results, she wins the prize. The experiments are rolling a pair of dice, tossing 3 coins, or spinning. So what this really means, all right, is that if she chooses, she has to choose one of these 3 games, all right? And if she rolls or spins or flips 3 identical numbers or identical numbers whenever she does this, she wins. So she has to try to figure out which experiment is best for rolling the exact same values, because that's what she wants. She wants the outcome with all matching results. That's what she wants. She wants all matching results. So a dice being identical, all 3 coins being the same thing, or both spinners landing on the same number. So in order to do this, the first thing we have to do is we have to look at the sample space of each one. So I'm going to make the sample space really quickly. You may have to pause it and go back, but again, that's what's the best part about this video. So So for the die, the sample space for the die is going to look like this, all right? Again, I'm going to make it look like this, all right? So you're going to have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now here's the thing. You can fill out this entire die, all right? But what I'm going to do is I'm going to fill it out a little differently, all right? I'm going to think about like, all right, if I'm trying to get identical pairs, am I going to look at like 1, 3? Like if I roll a 1 and I roll a 3, is that good? No. But I'm going to look at it as like 1, 1. Like I roll a 1 first and I roll a 1 second. So sometimes you will see this probability like table that I make here using like, it looks like coordinates. That really just means like the first, I roll the first guy here and then the second guy here. That's what the coordinate means. So 1, 1 is a good outcome. That is a good outcome where you get identical events. Another one is 2, 2. Then 3, 3, 4, 4, 5, 5, and 6, 6. There are no other ways that you can roll die and get identical events. So there actually are 6 good outcomes here. So 6 outcomes that help us out. So 6 outcomes. That isn't even spelled correctly, but whatever. All right, so 6 outcomes when you roll dice. Now, flipping a coin, all right, that right there, we're going to need to list out that sample space. Well, you can have head, 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 tail, 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 right? These are the only 2, tail, 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 that you're going to get that are successful. So you get 2 outcomes. But the one thing that we need is we need to know how many there are. Well, there's head, head, tail, head, tail, tail, head, tail, head, tail, tail, head, tail, head, head, and then tail, head, tail. So that's your sample space, but these are the only 2 good ones that we want because we need identical rolls or identical flips. So we get 2 good outcomes. Over here we got 6 good outcomes. Now with the spinners, I'm going to do the same thing I did with the die, and I'm going to create this. So I got a spinner, I'm going to get a 1, 2, or 3, a 1, 2, or a 3, and again, just like the die, 1, 1, 2, 2, and 3, 3 are all I really care about. Yes, are you going to get other numbers, but will those give you identical rolls? No. So here we go. So we get 3 good outcomes. All right, that's what we get. So now the question says, which experiment should Tanya choose to have the best chance of winning? So now right away people are like, well, 6 outcomes, that's the best one you want. Well, here's the thing. We have to actually look at the probability because you don't guarantee to get one of those 6 right away. You actually have a 6. So for this one, for this guy over here, for the die, you get a 6 out of 36 chance of rolling doubles, a 6 out of 36, because there's 36 total numbers. 6 times 6 is 36 total numbers. So this simplifies to 1 6, or as a decimal, all right, you want to try to look at that. Come on, calculator, turn on. 1 divided by 6. All right, so you're going to get a 1.6 repeated. So 0.16 repeated as your answer. Now, for the flipping coins, all right, there were 2 good outcomes out of a total of 8 possible combinations of flipping heads and tails. All right, so 2 out of 8 is actually 0.25. You look at that as a decimal in your calculator, so 0.25, which I look at that, whoa, that actually is a better outcome than the dice right now. So I'm thinking, hey, flipping the coin's pretty good right there. Now let's look at the spinners. Now the spinners, all right, there were 3 good outcomes out of a total of 9. You could have gotten 9 different outcomes because there are 3 spins you can get, 3 other spins. So 3 times 3 is 9. So 3 over 9 is actually 0.3 repeated. Holy cow, if I look at that, if I look at these answers, 0.6, 0.25, and 0.3 repeated, which experiment should she choose to have the best chance of winning? She should choose, drum roll please, the spinners. Okay, because the spinners are the best. The spinners give you the best odds of 0.3 repeated. The next step would be flipping a coin and then lastly rolling a die. Even though there were more outcomes that were good, you have a total, your sample space is so much bigger when you roll die compared to flipping coins or spinning some spinners. So this is kind of getting us to start thinking about different outcomes and different probabilities. So with that said, let's go to page 37. So let's go here. Now, all right, now for this first problem, all right, we're going to start talking about independent events, all right? Now, in this first problem, we are not doing any math. We're just going to think logically about this, okay? So it says, Miss Martinez is teaching her students about probability. She has a bag of 6 marbles. 2 of them are red and 4 of them are black. She asks her students to conduct the following experiment. So there's 2 experiments. Experiment A, all right, the first experiment says, pick a random marble. So here's experiment A. pick a random marble from a bag, so it could be red or black, and then replace it back in the marble. So you see it, and then you replace it back in, and then pick another marble from the bag. All right? And then experiment B, the second experiment, all right, is you pick a random marble from the bag, you look at it, and then you do not replace it. So you hold that marble in your hand, and then you pick another marble from the bag. All right, so it says, for each experiment, determine whether getting red on the first pick and getting black on the second pick are independent or dependent events. So, all right, number one, it says assign variable names for the events. All right, so basically, what I would say is RM is red marble. Man, I'm gonna spell this poor. Oh, marble. I spelled it right. Red marble, and then black marble. So BM is black marble. All right, now, so that's just oh, they named it RF and BS. So let's change this because I kind of messed this up. So I guess there's a bunch of different names that they want you to choose. You can name your red marble, black marble, but they're using these down here, and this is what I just noticed. So they have RF and BS. So RF means that you get a red first. So you pick a red first. And then BS means black second. All right? Because those really are the two things that are happening. They want you to see, will you get a red marble first and then a black marble, how that works. So that's how you label them. And it says for experiment A, determine whether getting a red first and a black second are independent events. So thinking about this, all right, if you think about it, we have 6 total marbles, 6 marbles, MARBLES, all right, 6 marbles. You have 2 red? Where is it? 2 red. Yeah, there we go. So it's 2 red and 4 black. All right. Now, if you think about it, in the first one, all right, if you pick a red first, all right, in experiment A, you pick a red first, all right, so your probability is 2 out of 6 to pick a red first, all right, picking red first. And then in experiment A, you put your marble back in. So what happens is your next pick is still out of 6. You still get 6 more marbles to choose from. And so that next choice for a black second is a 4 out of 6. You get 4, there's 4 black marbles left and 6 total marbles to choose from. So these two events occurring, these are independent right now. Independent. Because it doesn't matter what this first marble is. Yeah, we want it to be red. Great, we want it to be red. But it doesn't really matter because once we put back the marble, once we put it back, the second pick for the marble it doesn't even matter. It doesn't matter if you picked, a green marble. There's no marble there. That's green. But you pick a green marble. It doesn't matter because once that marble goes back in, they're independent events. Nothing's changed. We're still working from 6 total marbles and 6 total marbles. So because we put it back, this experiment is independent, all right? So there is no math, but I'm just showing you this. Now, experiment B, again, still working with the same 6 marbles. Well, it says you pick a red first. So, that's a 2 out of 6 probability. You have a 2 out of 6 chance of picking a red. Now, it says that you keep that marble. So you're hoping that you get that marble. So if you keep a marble from that bag of 6, how many are left? Well, for the second pick now, you only have 5 marbles to choose from, but there are still 4 marbles left. So because of this change that we have, because we kept this marble, this has changed from a 6 to a 5 marbles left. It's changed the probability, or what probability you actually have of choosing a black marble. So because of this change, they are dependent. And the book wants you to try to think about it logically first, to think about independent and dependent. And if you hold a marble, if you keep a marble, and it changes the entire process or the entire experiment, clearly that first action is making the second action dependent on it. It's dependent on, did you get a red marble or did you get a black one, because it changes everything up. All right, because you hold on to that marble in your pocket. So it's dependent. So it's a little confusing, a little crazy, but this next one on example number 2, all right, you are going to actually use the independent property or the independent rule. All right, so here we go. Example 2, it says Trevor loses or tosses a coin 3 times. Consider the following events. So right away, as soon as I see this, this is what I'm doing. All right, I am going to draw out my my sample space. I'm just going to do that. So you toss a coin 3 times, so you're getting a coin. So you can do, all right, heads, 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 tails, heads, tails, tails, and heads, tails, heads. So that's the combinations of getting heads first, and then you can do tails, 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 heads, tails, heads, heads, and tails, heads, tails. These are the this is the sample space when you toss a coin 3 times in the air. So this is what we have. We got eight total things. We got 8 things here. 8 things, or 8 outcomes. That should be one word, but I didn't have enough space. Anyway, all right, so we got 8 outcomes. Now it says, consider the following different events. So the first event is A, and they call it first toss. The first toss you have is heads. So that means the first letter in the combination is H. All right. B is the second toss is heads. So that means the second letter in the combination is heads. And then C, all right, C, we'll do this one in green. All right, there are exactly 2 consecutive heads. That means there has to be back-to-back heads, not 2 heads in a combination, but it needs to be like heads, heads, tails, or tails, heads, heads. Like heads have to follow each other. All right. Anyway, so using these 3 different events for each of the following pairs of events, determine if the events are independent. So this is what we do. First off, it says, are A and B independent? So this is what we're looking at first. So what we're going to test is we want to say, hey, is the probability of A intersecting B equivalent to the probability of A times the probability of B happening? So that's what we have to look at here. All right, so what we're going to have to do is we're going to actually have to calculate some of these values. All right, so let's start with A. So let's look at the probability of A happening. All right, now I know my probability of A. All right, probability of A is going to be out of 8. So I know it's going to be out of 8. All right, now the probability of A is the first toss is heads. So if you look here, how many first tosses are heads? Well, if you look, 1, 2, 3, 4. 4 of them, 4 of your first tosses are heads. You have a 4 out of 8 shot to get your first toss heads. Now B, the probability of B happening, B is the second toss is heads. Well, you look here, now that we have them listed, second toss, 1, 2, nothing over here. Okay, TT, no. Okay. Oh, here we go. 3 and 4. So again, this is a 4 out of 8. That's my probability. So now, for this to be independent, all right, what we have to do is we have to look at the intersection of both of these happening. Well, I know it's out of 8 again, but let's see. All right, A intersecting B. So that means we have to find how many of these have the first toss is heads and the second toss is heads. We're looking for both those. So first toss heads, second toss heads. Boom, that's 1. First toss heads, second toss heads. Boom, that's 2. No, 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 no. Okay, so it's 2. So it's a 2 out of 8. So what we do now, all right, is what I do is I look at this in my calculator. So I will convert 2 out of 8 into a decimal. So 2 out of 8 is 0.25 equals, and what I'm going to do is I'm just going to multiply these bad boys in my calculator. All right, parentheses 4 over 8 times 4 over 8 is 16 out of 64. Let's do this in my calculator. 16, 64. Boom, you get 0.25. So we're getting 0.25 here. Hey, these are equivalent. So because they're equivalent, what we can say is this is independent. Hey, those 2 events, A and B, are independent events. Awesome. Now, let's try the next one. All right. Now, many of you might be writing and pause it. I'm going to erase all this stuff and I'm going to get started again. All right. So let's get rid of this guy, get rid of these things. Okay, so here we go. Now let's look at the second one, A and C. So A and C again. Now we already have the probability of A. So we're going to rewrite this. So the probability of A intersecting C, not B, good. All right, C is equal to the probability of A times the probability of C. Now, if you look at the last problem we just did, we already had to find the probability of A. We had to do that. So we know that the probability of A is 4 out of 8. I got a 4 out of 8 shot here. Now the probability of C and the probability of A intersecting C, we know those are out of 8 also. Let's figure out how many there are. So we go back to our sample space, and we look, all right, probability of C, what's C? It says there are exactly 2 consecutive heads. We need exactly 2. That's the big thing, exactly 2. That means you can only have 2 back-to-back heads. So this first one, H, 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 that is not one of them. You do not include that. But we will include this, HHT, exactly 2 consecutive heads. No here, no here, no, no. Hey, that works, THH, and no there. So for the probability of just C happening, that's a 2 out of 8 probability. Now, let's look at this last one, all right? So we have to find the probability of A intersecting C. So A intersecting C. So here's A intersecting C. So the first toss is heads, and there are exactly 2 consecutive heads. So let's look. First toss is heads, exactly 2 consecutive heads. So I'm going to highlight this one, all right? First toss is heads, exactly 2, no. First toss is heads, exactly 2, yes. Heads is my first, and exactly 2, good. All right, no, 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 no. Oh, let's look at the one that we circled also. First toss is heads. Oh, no, that's a T. So we don't include that. So this is actually a 1/8 probability. So now, again, we multiply these all together over here. So we put these in parentheses. We're multiplying. 1/8 in your calculator, all right, just because it's easier with your fractions, is 0.125. And now when we multiply these guys together, all right, in your calculator, you should get 0.125. Hey, those are identical also. So these are independent events. So A and C, these are independent. So the first one was independent. The second one is independent. Well, the third one must be independent, doesn't it? Well, we'll see. So I'm going to erase this. All right, and we're going to try the last one. Let's try the last one now. So B intersecting C. That's what we're going to want to see. So I write out my independent event formula. So the probability of B intersecting C, all right, BAC. B intersecting C is equal to the probability of B times the probability of C. All right? So let me clear my sample space. Let me get rid of the highlighter and all that stuff. All right, so let's get a clean sample space. So now, one cool thing, we actually found the individual probabilities of B and C already. We know the probability of B is 4 out of 8. The probability of C is 2 out of 8. We got that from the last problem. And then now we have to find our probability of B intersecting C. So B intersecting C is the second toss is heads, and there are exactly 2 consecutive heads. So we need the second toss heads and exactly 2 consecutive heads. So we look here. Second toss is heads. So we can only look at this, no, 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 no. Second toss is heads, second toss is heads. All right. So we can only look at the ones that we circled. So we need second toss is heads and exactly 2 consecutive heads. Well, I got head, good, but oh, there's a third head. So no, boom, that's out. Head, all right, and we need exactly 2 consecutive heads. Ooh, this works because it's head, even though the first one's heads, that's fine, all right? No, let's look down here. THH, hey, second toss is heads, and there's 2 consecutive heads, that works. And then the last one, nope, there's not 2 consecutive heads. So this actually is a probability of 2/8. So now let's simplify these decimals. So 2/8 is 1/4 or 0.25. Now when you multiply these, 4/8 times 2/8, that's 8/64. And you get 0.125. Wait, are these two equal to each other? That answer is no. So since these two don't give you an equal or a true statement, this is dependent. So this one is a dependent event. So this B and C, so the second toss is heads, is going to have a dependent effect on having exactly 2 consecutive heads. These are 2 dependent events here. So we can see that and think about it, but you can also see it algebraically that they're dependent one on each other. All right, so here we go. Example 3. Good Lord, if you didn't think we were working long enough, here's our last one. All right. So this is about buying food, and this is on your homework, so we want to make sure that we're good on this one, all right? So Landon owns a delicatessen, that's a deli. He collects data on sales of his most popular sandwiches for 1 week and records it in the table below, all right? So here we go. Sandwiches sold in a week, so you have different choices of sandwiches, like Landon's Club, turkey, melt, blah, 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 blah. And then you get a bread choice on the left side. This is called all right, a frequency table. Now, in all frequency tables, when I see this, you need to find your marginal value. And marginal value means you need to add up everything going downwards in each column and everyone going across in each row. So I add up all the Landon Club people. All right, I add up all the turkey melt people. I add up all the roasted chicken. So you want to know all these values before you even start this or read anything, all right? So we're going to add these all up. So 44 plus 24 plus 24. So you're going to get 92 here. 25 plus 28 plus 27. You're going to get 80 here. 25 plus 26 plus 24 is 75. Ooh, hard to read that. And then 8, 31, and 34. 8, 31. So you should get 73. Now, that's not enough. We actually got to keep adding them across, too. We need to know our rows also. So you got to add how many people got country white? So you got to go like 44 plus 25 plus 25 plus 8. So you get 102. Add up your whole wheat. 24 plus 28 plus 26 plus 34 is 112. And then add up your sourdough. 24 plus 27 plus 24 plus 31 equals 106. Now, the last thing I always do is I get a grand total. So a grand total of people or items purchased. So what you can do is you either add up everything going downward or everything going across in these green numbers. So I'm just going to go downward. So 102, 112, and 106 added together, and you get 320 total sandwiches. And you'd get the same thing if you added up all the numbers going on the bottom, 92, 80, 75, and 73. You get 320 also. All right, so you need these numbers. You need these because now with all these numbers, we can now try to figure out independent events and dependent events. So I'm going to scroll down some more so I can see. Oh, God. There we go. All right, so now it says each of the following statements describes a pair of events. For each statement, determine if the event seems to be independent based on the data or dependent. All right, so we're gonna check this bad boy out right here. All right, so oh boy, I'm gonna drop that. So I'll put that down. All right, anyway, so here we go. Let's start with this one right here. We're gonna start with this guy. So like for right now, don't cross this out, but I'm gonna like cross it out just so you're like not thinking about it. But we will do that one. We're just gonna focus on this one right now. So we want to see if these are independent events. So a random customer orders Landon's Club sandwich on country white bread. So what we're looking for is Landon's Club sandwich. Is that independent or dependent with country white bread? So this technically is like your probability of A, and this is technically your probability of B. All right. So we're looking, are these two independent or dependent? So what we have to do, all right, so what I do is I do the probability of A intersecting B is equivalent to the probability of A times the probability of B. Oh, I wrote that really weird. Put parentheses there. Times the probability of B. So, all right, so when we talk about A, in this case, notice I wrote Landon's Club sandwich. I put a P of A, so that's what we're going to be talking about. So here we go. First off, now let's talk about Landon's Club sandwich or probability of A. All right, that's what I'm calling it right now. So the probability of somebody choosing that is going to be out of 320 people. All of these are going to be out of 320 because 320 people were our total survey population. They were out of 320. Now, for Landon's Club sandwich, that is up here, Landon's Club. How many total people would choose Landon's Club sandwich? So we go all the way down here to 92, and that's what our probability is. If we were to choose somebody randomly, 92 out of 320 would choose Landon's Club sandwich. Now, it could be on any sort of bread, but they're choosing that sandwich. Now, country white bread, so now we're doing country white bread. If you look at country white bread, now we go all the way across and we say, how many people have got country white bread? Now, it could have been on Landon's sandwich or the turkey melt or chicken veggie, whatever it is. All right, that's 102 people. So this right here, these two probabilities, we're going to look at these and say, all right, well, if they are multiplied together, will they equal the probability of their intersection of somebody getting a country white sandwich with Landon's Club on it? So that is right here. This is our intersection right there, 44. 44 is our intersection because that's where these two intersect. Landon's Club and Country White. 44 people got both of those things. So what we do is we say, all right, let's go 44 divided by 320, and you get 0.1375. Ugly 5. All right. So that's what the probability of the intersection, both of those happening at the same time. So what we do is we're going to take these two, the probability A and the probability of B, and we multiply them together. Make sure you use parentheses. So 92 over 320 times 102 over 320. And you should get a decimal of 0.0916. So looking at these two, are these two events dependent or independent? All right. So here's the thing. All right. These right here. All right. These right here right now. These are technically going to be considered independent events, or dependent events, because these are not equal. These are dependent. Now, here's the thing. All right. When doing the probability, and this book is awesome with it, sometimes your probability are going to be very, 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 very close, but not identical. All right. A lot of times when you have bigger numbers, it's very hard to get them identical. If we're within like 1/100th or 1/10th, all right, maybe 1/100th, so to the second decimal place. If we're off like 1/100th, the second decimal, if you're like off 1 or 2, that's fine. In this problem, we're actually off like 4/100ths. So I'm going to say that that's dependent. These are not equal to each other. But if it was a little closer, I might say that it's independent. All right. The book kind of stinks with that, especially on their homework. Like the homework, you're going to notice that one of the problems you're going to get, your two numbers being very, very close, and they're actually going to say it's independent. So they choose when it's independent or dependent. These are too far away, so these are dependent events. All right. So now let's do one more. Let's do the second one now. All right. So I'm going to do this one, the second one. All right. So for the second one, all right, let me block this out so you can't see this anymore. Come on, scroll down. I don't want to erase it. All right, here we go. All right, so now what we're going to do is we're going to say our random customer orders the roasted chicken sandwich. So now that's going to be our probability of A. And whole wheat bread, that's going to be our probability of B. And now we're going to go ahead and do literally the exact same thing we did. So we're going to say, all right, well, the probability of A intersecting B must be equal to the probability of A times the probability of B. All right. So we go through the same thing. Everything's out of 320 total guess. All right, out of 320 times out of 320. So now we just need to find their individual events. So let's start with individual ones first. All right. So let me get rid of Landon's Club. We're done with Landon's Club. Get out of here, Landon's Club. Get out of here. Okay. And get rid of that. All right. So now, all right, let's start with roasted chicken. So roasted chicken is right here. Well, how many total roasted chickens did we have? That's 75. So your first probability is 75 out of 120 or 320. And then whole wheat bread, here's whole wheat bread. So we go all the way over to how many people got whole wheat bread? That's 112. All right. And now how many people got both roasted chicken on whole wheat bread? Hey, look at that. That's 26 out of 320. So just like we did on the last problem, we're going to multiply our two individual probabilities together. So 75 out of 320 times 112 out of 320, and we're gonna get you get 0.0832. Nope, 203. Dyslexia's getting me. All right, so 0.08203, and now on the other side, 26 out of 320. All right, this is 0.08125. Now, if you look at this, all right, these are not identical, but look, they're so close. These are like literally 1/1000th off. So we're going to say this is good. This is true. All right, so these are independent. All right, so they're independent of each other. So clearly getting roasted chicken, it doesn't matter if you get roasted chicken. It doesn't really mean that you have to get whole wheat bread. All right, so notice how close those were. Those were much closer than the last one. So those are independent of each other, getting whole wheat bread and a roasted chicken sandwich. All right, so this has been a long time. I didn't think it was going to be this long, but whatever. Please make sure that you are doing your homework. You're checking your answers in the back of the book. All right, and I wish you guys the best of luck. Make sure that you are checking your answers, all right? And check Google Classroom because I'm going to be putting the answers up on there as soon as I finish those. So make sure you're looking at that, and please be good to the sub. All right, I'll see you guys when I get back.